Great. Okay, so this will be Machine Learning Lecture 3. And now that I've gotten a lot of overview out of the way, I dispensed with this optimization question very pragmatically and quickly, and I've just avoided giving you very much information about statistics and information theory. And so the sort of one remaining topic that for the third lecture I'll tell you about is some stuff about how to think of neural network architectures. So up until this point, I've emphasized this idea that machine learning is really, really simple. You have a high-dimensional input as some vector, and then you can do the most natural thing possible to construct a simple nonlinear function of it by hitting it with some affine transformation with some matrices and a simple nonlinearity. And so the question is sort of what else might you do? Do you ever want to do something more complicated than this? And why? And what are the considerations you should keep in mind when building some kind of more complicated neural network? And I think this has several components. You can view it in a very sort of ML AI person. You can view it through a very ML AI person lens, and I think a lot of those people tend to think about it in terms of, oh, well, like I'm imitating some neural system, or you can think carefully, well, like what is the process I'm going through when I solve a problem, and so let's build a neural network architecture that does that same kind of thing in miniature. Or you can take a very pragmatic perspective, which is you have data, and maybe your data comes in a really, really, really high dimensional vector. Like you have an image, as I mentioned before, that has 1 million pixels, or you have several pages of text with hundreds or thousands of words. How do you sort of get all of that information into a neural network and process it without having, say, million by million matrices? You don't want to have a million by million matrix. So how can you sort of pragmatically break the data down into some subcomponents and break the architecture down correspondingly to have a manageable number of parameters that make sense? So there are a lot of questions that you can think about. I think maybe the number one question, and a source of many of these more highly cited than ADS-CFT type ML papers, using extremely basic ideas, is sort of the question of information propagation. By which I mean, when you send a signal into this neural network, is it blowing up or decaying to zero very quickly, or is it staying sort of an order 1 signal throughout the network so that the network can continue to sort of make progress on processing it? So I guess there's two directions here. There's the direction of signal from input to output. Does the signal actually get through? And then there's the sort of very, very closely related question of the gradient with respect to the neural network parameters is well behaved and well defined. So if your signal isn't getting through, then that means that some gradient with respect to parameters of your loss is going to be either really big or really small, or there are going to be large hierarchies in the gradient, and that isn't a very healthy thing to do because you're using gradient descent to update your parameters. So if your gradients are 0, you don't learn. If your gradients are exploding, then you also don't learn because you don't update your neural network, you don't learn in a way that is useful. So I think this is a sort of number one thing to consider. There are a bunch of incredibly basic ideas from the literature that help to address this, but it's something to keep in mind. Other considerations you might have are do the symmetries match? So, for example, if your data is an image, You might expect images to be roughly translationally invariant, not that a specific image is, but the way that you process an image doesn't really depend that much on where in the image you're looking, and so you can take advantage of that to reduce the number of parameters you use. Similarly, if you have a sequence of words, the way that you think about the 10th word in the sequence and the 20th word in the sequence isn't so different. Of course, they differ by what context you have, but you might expect that there's some translationally invariant operation that you can perform, again, to sort of reduce the total number of parameters you have in your network. Related to this, kind of related to both of these, was a question of does info propagate efficiently? That is, in, say, a small number of steps. So one kind of network that we'll talk about briefly are recurrent networks. And what recurrent networks do is very intuitive. If a recurrent network were to read the board, it would say, it would look at information, and then it would remember something. Then it would look at propagation, and it would add that to its memory in some way. It would look at then signal, from, input, to, output, etc., and it would go through this text, remembering something, updating its memory each time as it went from word to word to word. Now, this is, when you think about it mathematically, a bit dangerous, because if you read 1,000 words, it's hard to remember what you saw in the first word. Why would it be hard to remember? Well, literally, these networks are doing some kind of linear algebra operation, which means they're multiplying by a matrix, and then they're doing some nonlinearity, which is more mysterious. But at multiplying by matrices is something we really can understand. And if you multiply by a matrix 1,000 times, you know what the answer is that you get. You get something that's dominated by the biggest eigenvalue of the matrix, unless it's orthogonal or unitary, etc. And if it's orthogonal or unitary, if you multiply 1,000 times, if it's a fairly complicated orthogonal or unitary, you're going to get something that's very scrambled. So that suggests an issue that if I need to remember that I wrote information propagation 1,000 words ago, after 1,000 matrix multiplications, it may be very hard to recover that information. So you might think that an architecture that allows you to sort of access this text with only, say, 5 or 10 steps of processing instead of 1,000, if you're 1,000 words away, will do better if this information, if literally this text is useful 1,000 words hence. So this is also an important question. Related to one, but not necessarily identical. And they're related also, related to pragmatics, there's a question of is training computationally efficient? And I'm not going to say very much about this. The ideas I'll tell you about happen to be able to be realized, but this is something that you do have to consider if you're dreaming up some new architecture or some new training process. Usually, is training computationally efficient is mostly a question of, is it very parallelizable, or there are a huge number of sequential operations that create long chains of dependencies so that you can't train your network kind of all at once in an effective way. So for example, at least at 0th order, if you have a network that, say, looks at an entire page of text all at once and processes kind of all of the words in parallel, that is more efficient than if you look at the first word, the second word, the third word, etc. in sequence, because if you have 1,000 words, you have 1,000 steps. Whereas if you can look at all of the words in parallel and get some overall impression, then maybe you only have a few steps. You look at all of the words together, you process them a few times, and you're done. That might be much more efficient. And we'll see architectures that do these various things. There are also some other more theoretical questions you might have, like, can your network actually represent the function you're trying to learn? Most often, the function you're trying to learn is something extremely complicated. You don't have it in mind. But I mean, if you're trying to learn the function e to the x, it's hard for linear algebra to efficiently represent e to the x. And and even with these ReLU discontinuities. And so you might think that your neural network is not going to do a very good job. And typically, we don't even really think about this kind of consideration, but I mean, it's something that's natural to ask about and to have in mind. Maybe the task you're trying to train your neural network to accomplish is actually outside the class of functions the neural network can represent. But in practice, people don't really worry or talk about this very much. Yeah?
So I'm trying to understand something about the information propagation.
Yeah.
But the thing is, when you've gone through 1,000 operations and you want to get back to this fifth or sixth, so I mean, can one do like after some steps, one can take a snapshot and save in some volatile memory or swap, and you get it. I mean, does the architecture does something like that, or
so I mean, there are recurrent networks that, so I'll tell you very briefly about recurrent neural networks. There's something called an LSTM that I won't talk about because I'm going to talk about something else instead, basically, that's more complicated, that attempts to have something more like a long-term memory. It tries to have some kind of memory that isn't easy to destroy and therefore should be preserved longer. In practice, it still sort of suffers from this issue. There are also ideas where you have a neural network that's actually equipped with something like an external memory, so the neural network can sort of like read and write to some big hard drive. There's, I think the first sort of well-known version of this is the neural Turing machine. Does something like this. So that is certainly a possibility, but most of those things aren't used a lot in practice, but it's certainly something you can do. I mean, you can represent with a sufficiently complicated neural network and a sufficiently complicated training procedure all sorts of different things. The real question is sort of whether or not the loss, which is this thing you're trying to minimize, which is telling you whether or not your neural network is actually accomplishing the goal, is the loss differentiable with respect to the neural network parameters, even when you travel through all of these different operations. And that's where things like reading and writing to an external memory might become tricky. Any other questions? And whether or not the symmetries match is sort of related, this is often referred to as a question of inductive bias, which is supposed to be a good kind of bias. Which is really just a way of saying that maybe I want to bias my neural network from the very beginning towards being optimized to naturally accomplish some task. Okay, so now let's talk about some aspects of and solutions to this sort of info propagation question. So one thing that I actually already mentioned is that people used to train neural nets with activation functions that looked like this, and now they mostly use this function. And one reason for this that I mentioned is just that if you have a function like tanh that has a derivative that vanishes out here and out here, information may not propagate in the sense that your derivatives may just end up being 0 over large regions of parameter space. So this question of activation functions is something to consider, and it is believed that the reason why this is so much better to use as compared to that is because information propagates better. Another question you can ask, and pretty easily address, is the question of initialization. So if I have a neural network that involves these compositions of where the output of the n plus first layer is this ReLU, like this, then I have to start somewhere. And therefore I have to define on when I'm just getting started in the learning process, what do I choose for W and B? And that's a place where I could immediately sort of screw up information propagation. If I make the norm of W too big or too small, then I'm going to end up either blowing up my signal as I propagate through the network, or killing it. And I don't really know the history of this. This is a very, very simple thing to try to treat. But there certainly are papers that are very highly cited that talk about this. I mean, I know there are papers from the last 5 years, for example, by Kaiming He, that talk about this question. It seems so basic that it must have been also known in the distant past when people studied neural networks in the 70s and 80s. But anyway, how should you approach this? Well, you can imagine that recursively, that say your activations, this X that you're getting at the nth layer, these are typically called activations at nth layer. And this is the thing that you get out at the n plus first layer. You can imagine that these are, say, some random numbers that are order 1. What if they're not random numbers that are order 1? Well, your input is something that you have some control over. Like if your input is an image, then there's some pixel intensities that go, say, from intensity 0 to intensity something, and you can make that intensity something 1. So you can, in other words, by hand normalize your inputs so that they're friendly for your network. And then at the nth layer, you can just try to preserve that overall normalization. We have this matrix W. We're going to initialize it to something. So this is going to be sort of some random matrix. And maybe the simplest thing that we can do is we can assume that it has entries that are just Gaussianly distributed with some variance, some sigma. And so the question is, what is that sigma? Well, if these are numbers that are, if this is a, let's say, a d-dimensional vector, and for simplicity, if this is also going to be a d-dimensional vector, this could be a rectangular matrix, then this is some d by d matrix. If these are sort of basically random numbers that are order 1, and these are Gaussian distributed with some variance, then effectively each entry that we get, at least before we apply max, is going to be a sum of d products of order 1 numbers divided by or multiplied by the scale of the variance that we choose for W. And so it's natural to choose a scale here so that just assuming Gaussian statistics, we get the same scale there. And so that's how we typically do initialization. Now you might worry about this max. It'll set half of them to 0, so you might add a factor of 2. But up to things like that, that's how we do initialization. And it's important that that we do this right if we have a large number of layers.
What about this? Maybe what's the width of this Gaussian?
Good. So we set the width of this Gaussian. So we set the width of the Gaussian for this random matrix. So sort of Wij will be chosen from some Gaussian of mean 0 with sigma. We set sigma as a function of d so that the normalization here is the same as the normalization there. So how do we do that? Well, any one of these entries, so if it depends on the normalization here, but any one of these entries, if these are, say, order 1, then x n plus 1 I will be max 0 Wij x n j. So in other words, here we have a sum on j from j equals 1 to d of numbers that are Gaussian, that are randomly distributed with random signs. And so we have a random walk. And so we expect this will have this will have a magnitude of order, the magnitude of these numbers times root d, right? Because if we random walk in d steps, then this will be of order sigma times root d. And so we can choose sigma to be of order 1 over root d in order to preserve these norms. So this is something else. So what else can we do besides initialization? So there are two other ideas that are really, really simple that have been introduced more recently. So I'll tell you about something called layer norm. So here we want to initialize so that we get a nice distribution here. Well, here's another solution to the same issue. I get out these numbers at layer n xi. If I want them to not to be in some range, then I can take x, I can compute mu, which is equal to the mean of the xi. So in other words, being explicit, the sum and I can compute some variance, sigma squared, which is the variance of these xi's as well. And then I can just I can define some new x hat in, which is xin minus the mean divided by the standard deviation. So whatever I do get out at layer n, I can just recenter it to have mean 0 and unit standard deviation. So this is called layer norm, performing this operation. You can basically view this as a way of changing the activation function. The activation functions that we've been using, this max 0x, is component by component. It doesn't use information about component I when determining component j, but we can make that slightly more complicated by subtracting the mean over the layer and dividing by the standard deviation of the layer, and that way we're guaranteed that the distribution of the x's at each layer is reasonable. And that's independent of the initialization. I mean, once we do this, even as the network learns, this will still be enforced on the network that this information can propagate. And so that improves information propagation at the cost of not allowing the network to change the mean and variance. Now, one way to deal with that issue of not allowing the network to change, maybe the network wants some big x's, is to just make the mean and variance trainable parameters that can be modified by the network as it learns. So this is also sometimes done. But that's that. So I think this paper probably has like thousands of citations that it introduced this idea. Yeah?
It's not bad that you're making values negative now for that Residual function. Taking a lot of values and bringing it potentially to 0 on the next.
So here, I mean that is an issue. So that's another reason to let the network learn a mean if it wants to sort of turn most of them on versus off. This can be applied after the ReLU or before. So I mean, this can be applied after, and then the next layer hits it with a matrix and applies ReLU again. But I guess the benefit outweighs the cost. So there are other variations on this. There's another one that's maybe more famous called batch norm that I'm not talking about because it's slightly more complicated. The idea of batch norm is to just perform these means and renormalizations in the batch direction. So instead of taking all of the outputs in a given layer, right, there's some d-dimensional vector that the network outputs. While I'm training the network, I provide the network with batches of data, like 100 different images. And so for each xi, I have 100 different xi's, one for each image I was training on, and I can use the statistics in the direction of the batch to shift the mean and renormalize. That was an earlier version. It's also extremely widely used. You can do it instead, but it requires this idea of having a batch to figure out what the statistics should be. Whereas layer norm is much cleaner because it's really just a modification of what the function is that the neural network computes once and for all.
Sorry?
Yeah.
So the mean and the variance have to be predefined, or do you have to compute them every step?
This is being computed every step. So now with layer norm, the actual function at some layer is you compute, say, ReLU of 0 w x plus b, and then you call this x, and then you then apply to this x, you compute x hat, which is x minus mean of x over d by square root of sum of x minus mu squared over d. You compute all of these things, and this whole x hat, which is the composition of this and this, is your output that goes to the next layer. So you have to compute this every time, but don't worry, it doesn't actually create much of an inefficiency. Okay. And then there's, I guess, a fourth idea. Let's see what markers work. There's a fourth idea along these lines that's also very famous, which is called ResNets, or residual networks, which is the idea that, well, if I'm really composing linear algebra and ReLUs over and over and over again, maybe I destroy information. So instead of x n plus 1, I is some fi of x n, I'll just compute x n plus 1 as x n plus f of x n. So in other words, instead of applying f, I'm going to imply 1 plus f, or 1 plus epsilon f. I mean, this may be small, it may not be small. So this will be my layer instead of this being my layer. That's what a residual network does. And this affects what the initialization has to be, because if I compose many, many, many layers, then the norms of the of x and f change. Of course, I can combine together all of these different things. So I can make this be this, or for example, I could make it be layer norm of xn plus f to try to preserve the normalization. But regardless, this is a thing I can do. And this definitely has like 10,000 citations. So this way, if my early layers sort of do something that isn't very useful, I still have a lot of the signal from the initial input, and my layer has the opportunity to sort of save the day, and vice versa. And so this allows you to train very deep networks with sort of 50 or 100 or even 1,000 layers, and not have signals blow up or decay. So this was a big advance when it was first introduced, but it's really simple. Okay, so that's all I'm going to say about this basic idea of information propagation, but it's really an important thing to worry about and think about. If you try to train a neural network and it's not making any progress, it's not learning, this is one of the main things that could be a culprit. The atom optimizer helps with this. I mean, note that the problem with stochastic gradient descent that I mentioned, maybe the biggest problem is that you could have regions where the derivative, where the gradients are very big, and the model learns very quickly, and other directions where the gradients are very small, and the model learns slowly, and the atom optimizer is trying to help to deal with that issue. Keeping the normalizations of all of the activations and parameters roughly at the same scale also helps with that, and that's what that's part of what this is doing. So bad information propagation leads to a very, very jagged, kind of unpredictable loss landscape, whereas having good information propagation means that if you plot the loss as a function of the neural network parameters, which of course you can't do in the million-dimensional space in which they live, but you can do it in, say, small subspaces, then you find that using these techniques gives you a loss landscape that's much smoother, which means you can sort of gradient descend or atom descend more efficiently. And usually these ideas are presented as a bunch of totally independent things. So like there are individual papers about all of these things, and they're usually treated separately, but they're really all aspects of this question of does information and do gradients propagate naturally through networks? So now I want to move on to the thing that most people think of as talking about neural network architectures, which is actually talking about what functions we use these basic ingredients to compute in order to actually learn. So I'm going to talk briefly about RNNs, and then I'll talk briefly about convolutional networks. And I gave you a reference to LSTMs, which I don't know if you got an email, but it's at least on the sort of school website, I think. And then I'll attempt to talk about networks called transformers, which have been really very, very influential. I think maybe the transformer paper is the most important paper in this field from the last 3 years. And these are really, really widely used. They've largely, not entirely, but largely replaced these ideas. And there are many situations where they effectively can replace these as well. So I think they're a thing that's worth knowing about. And the thing that they help with the most is this issue of long contexts that I alluded to before. But anyway, let's first talk about RNNs. So let's say I have a sentence to model. So now I do. How do I actually try to learn how to predict how to write sentences? So first of all, I have to decide on some way to get the information about this sentence with, say, these 1, 2, 3, 4, 5, 6, 7, 8 words into some vector space. So the typical approach to this is to have some vocabulary with, say, just to make up a number, 50,000 words, and then represent each of these 50,000 words as a basis vector. So in other words, the might be 1, 0, 0, a might be 0, 1, 0, etc. Platypus might be 0, 0, 0, 1, 0, blah, 0, etc. And all of the words that I include in my vocabulary correspond to one of these unit basis vectors. Now, 50,000 is too big of a vector space for me to work in. I don't want to bother with this. So I make an embedding matrix E, which is 50K by, say, something more manageable, like, I don't know, 256. So I make an embedding matrix which embeds this very unambiguous information about which word I'm talking about into a 256-dimensional vector space where the vectors get all jumbled up in whatever order they want. And this embedding matrix E is something that I learn. So it contains 256 times 50,000 parameters. Those are all neural network parameters that I learn. Its whole job in life is to just be a linear operation. There's no ReLU or anything like that. And so I take the representation of these 8 words, and I get some vectors vi. Actually, let me write this in a more intelligent way. V S E is the embedding matrix E comma, I'll call it V, little v for vocab, of sort of the word S vocab, my word, where S is just some position. So S is 0, 1, 2, 3, 4, 5, 6, 7. And this V index is just this 50K dimensional index. And E, this is the embedding index. And this is the sequence index, which just tells me what position in the sequence my word lives. So now I have something slightly more manageable. I have 8 256 dimensional vectors, each representing the words. And these embedding matrices themselves are really cool and interesting. I mean, in earlier eras, they were just sort of something that people studied all by themselves. They do interesting things, like you can often find that vectors in this 256 dimensional space have real meaning. So like man minus woman may be roughly equal to king minus queen, because there's some vector that represents changing gender from one thing to another. There are all sorts of other things like that, like Washington, D.C. minus United States might be equal to London minus England or something like that. So there's a lot of semantic information in them, and they're quite cool. I'm not going to talk about them separately, but once you train a neural network, they typically contain a lot of kind of cool stuff. So that's just the starting point. Now we have these sequence vectors, and we want to do something with them to learn how to predict next words. And so a recurrent neural network is something that very naturally reads a sequence. So maybe it's easier to just say it here. I now have sort of V0, E, V1, E, V2, E, etc. After acting with this embedding. So my recurrent neural network will have a hidden state vector H. And all it is the recurrent neural network is a machine which outputs H n plus 1, which is equal to a ReLU, say, of 0, W. This is this sort of RNN's W, which acts on the concatenation of V n and Hn. So this marker is dying too. So what's going on here? Well, what the recurrent neural network does is it starts out with some initialized H, say H equals 0. And so sort of here, H is 0. And it takes in V0E and this H, its initial H. And it outputs a new H1, and it gets in V1, and the RNN acts again, and it produces a H2, and then it gets in another V2 and acts again, etc., and produces an H3, and on and on and on. So this is a very, very simple thing. This W and B are the neural network parameters for the recurrent neural network. This is note this is a rectangular matrix because it takes in something. This V was 256 dimensional. H could be whatever we want, but maybe it's, say, 256 dimensional as well. And so this will be a 256 by 512 matrix that keeps acting on new information plus its memory to produce a new memory. So so this seems kind of like a closed system. This is just producing memories and taking in new inputs. So how do we get something useful out of this? Well, at each point, we can sort of pull off H and feed it into something that does something useful. And the most standard useful thing to do is to predict the next word. So we can add, say, some simple neural net function just to sort of digest H. So we can add, say, some extra nonlinear function of W times H plus B. This is some separate thing, so I'll say this is some fully connected part. And this then gives us some matrix Y, some vector Y. And now we'll just take Y and multiply Y by E. Maybe it's E inverse. Or E transpose, really. And when we do this, we get back a vector which is a 50,000 dimensional vector. After acting again with E, we restore ourselves into the space of words. And so now we have a 50,000 dimensional vector in the space of words. And we can then go and interpret that as something that gives us the probability that the next word is any of the 50,000 possible words.
How can E have an inverse if it's 50,000 on 100?
So it doesn't have an inverse, it's just the transpose. So it's just a 50,000 by 256 matrix. We can view it as a mapping from well-defined discrete words to this 256 dimensional vector space, but it also is a map from this 256 dimensional vector space to possibilities for words. So note that we don't have to use the same E here. So if we want, we can have a E input and an E output, and that's a choice. If we have two of them, then we have two big matrices hanging around, but that's perfectly fine. So this could be E output, and we could use E input here, or not. It's common to have them be the same matrix and just sort of force the network to kind of sort things out, but you can make them different if you like. And this is then our how we make our predictions. Just to remind you, we're just going to take this thing. We're just going to take this thing and compute. So we have this Y, E, E out, E comma V, and we're just going to compute E to the that over sum on V prime of E to the and we can interpret this as some probability P for each V, where V is indexing what word we have in the vocabulary. And so this gives us 50,000 numbers that add up to between 0 and 1 that add up to 1. And those are going to be the probability that the next word is say. So when I say let's, hopefully if the model is well trained, say is reasonably probable, I have, etc. And that's how we can train. And we can run this network on a sentence in order to write as well. How do we use it to write? Well, we start with let's, and then we ask the network for its probability distribution of the next word, we randomly choose or sample a word from that probability distribution. We say that's the word. We feed it back to our network once again. We ask it for its prediction for the following word, et cetera. And that's how we would use this model to do writing. So I really have spent more time telling you about the sort of setup than about recurrent neural networks. That'll be useful, but the recurrent neural network is just this incredibly simple, dumb thing, which is just this matrix, which is a rectangular matrix, so it's just some one-layer network. And there are all sorts of fancier things you can do with this, like you could have multiple recurrent neural networks. So I could put another neural network below this. Instead of having this H go directly to an output, I could run a whole other line of separate recurrent neural networks that take the output of this one and as their input and produce another input, and I could stack them on top of each other like that if I wanted to. So this is just some basic atomic unit that I can plug in for this purpose. And its problems are basically just this issue that this hidden state is the way that it remembers. So if it's trying to predict model here, and it wants to remember something about what I said earlier in the sentence, or maybe in some sentence in the past, it has to sort of have not destroyed that information via these successive matrix multiplications. There's this thing called an LSTM, which is a more complicated version of this that tries harder to not destroy the information. In practice, it's not that much better, but it's somewhat better. Typically, it's better just because it's easier to train. It's more stable. So questions about this setup or what the RNN is? Yeah?
So you're taking this huge vocabulary and projecting it to some smaller subspace that presumably holds information about what the sentence could be about. So this is like a one-layer network, right?
Exactly. So when I mentioned stacking another RNN here, that would make it sort of like a two-layer sequence modeler.
Right, so would you take that 256-dimensional thing and project it to something smaller, keep it the same size?
It's all up to you. I think the most common practice would be to then keep it the same size as you go down. If you're going to use more layers, but anything goes, and I mean there isn't a ton of so there's no theoretical understanding of what's better and worse, and there's some empirical understanding where there's sort of best practices that people have found, but I don't think there's like a prescription where someone's tried every single possibility and sort of figured out that like the best thing to do is have 512 here and 400 in the next layer and 300 in the next layer or something like that. Like it's sort of just depends on the data, and ultimately I think it doesn't really matter all that much.
So is there any sort of understanding as to when I may want to add more layers or keep a smaller amount of layers?
Well, so for this kind of task, basically I'm going to tell you that I'd recommend you use this instead of RNNs at all. But if you're going to use these, what I would recommend is you use an LSTM because it'll be more stable to train, and that you probably don't need more than one layer. One layer is surprisingly good, so maybe it's shocking if you do this process and you use one single fairly large LSTM. You'll actually get pretty decent results. So if you do sort of exactly what I just said, make this an LSTM. When I say big, I mean, I don't know, instead of this being 256, make it like 1,000 dimensional or something like that. You'll actually get pretty good results.
Did you define the acronym before?
RNN is recurrent. LSTM, it's called long short-term memory. That's what the acronym means, but I mean, it sort of doesn't matter. Except, I mean, everyone calls it an LSTM, and it doesn't, I mean, the memory part is sort of not that, I mean, it's not any more meaningful than just that H is this memory. What I would say, at 0th order, what matters for these things is once you have stability, once you're not like diverging, in other words, once information propagation is good and you're learning in a stable way, Basically, more parameters is better, and it's fairly smoothly better. And significant variations in sort of these kinds of architecture choices, like do I use 2 layers or 1 layer, or 3 layers? Do I make the layers different sizes or the same size? Are small sort of perturbations on how many parameters did I use. If you have a lot of data, so you're not overfitting is not the biggest problem you're facing, then just more parameters is better.
These are all like linear layers, right? So you're defined by some matrix just linearly, right?
Yeah, I mean, except for this ReLU thing, everything's linear.
So is it that this sort of model doesn't do anything, model nonlinearity?
Oh, it does model nonlinearities, right? Because there's this ReLU thing that, I mean, it sets everything negative to 0, and that's nonlinear, and it is able to compose those, right? So, I mean, when we said that this is a single layer, it's a single layer in this direction, but note it's like many, many layers in this direction, right? Because whatever information propagated in from here then gets processed many, many times before it then is used to make a prediction. So the number of layers is equal to the length of the sequence in this direction, but it's sort of basically order one, it's 1 except for this embedding in that direction.
So is there anything to stop you from using a different function other than like a max or a relative layer?
Nothing to stop you. I think that also, in the class of functions that sort of have a derivative out to sort of large values of x, I think there isn't a lot of variation in sort of how well you'll do, but you can try other functions.
So like you do like a ramp, and you do like tanh.
Oh, so I drew tanh as an example of things that people used to use and that I would recommend you don't use. Because basically the inputs, either if they're very big in the positive or negative direction, don't give you a derivative, and that typically leads to less learning. It's called saturation. So yeah, I mean, I would recommend you just use this unless you have some strong reason, something else. So I mean, we do use this function at the end to get a probability out, but that's sort of just at the end of all of this processing. Any other questions about this? Okay. So the other very well-known architecture is convolutional.
Can I use this to solve a differential equation?
Yeah. But like, you better have a lot of differential equations, and it probably should be pretty big. But modulo those two things, yeah, you can input the differential equation as like some statement in characters, and you can ask it to output the solution. And if you give it like 100 million differential equations to train on, and with their solutions, you'll probably be able to then give it new differential equations, and it'll give you solutions. I mean, there's a paper, I don't remember the name of the paper, I don't even think it's that great of a paper, that uses this, by this I mean transformers, but this basic idea, to do integrals, and it does integrals. It does better than Mathematica, like symbolic integrals. Okay, so how much time do I have? Till 4:15. Okay. Okay, cool. So let me tell you about convolutional networks, and then I'll tell you a little bit about this transform idea. So this is another thing that's very famous. It's used in many cases, but most often for images. So if I have an image, it may have, I don't know, a lot of pixels. Say it's 256 by 256. Today is 256 day. So I don't want to try to act on all of the information in the image at once. So how am I representing the image? Well, maybe I have, for each pixel just gives me a number. So that means that I have a vector space that's 256 times 256 dimensional. Now I want to use translation invariance. So let's make up an operation that I can perform that's naturally translation invariant and that has much less, many fewer parameters than I would have if I acted on all of these pixels at once. And the idea is to have a filter. So I can have a filter, and typically these filters are very small. A fairly big filter might be 5 by 5. And this filter is something that acts on all of the pixels in some 5 by 5 window. So in a 5 by 5 window, I have 25 pixel values. So I just have a 25-dimensional vector space. And that seems really, really great because now I can just act on that 25-dimensional vector space. And so I can map, I can define some W, C, I that acts on the xi, where xi equal pixels in the filter. And I mean, I can make this nonlinear, so I can do this. And now I can run this filter translationally invariantly over the whole image. So, in other words, I can calculate what this filter does in this region, then I can slide it over and act it in the next region and the next region, etc. I also slide it down, so I'll act it this, etc. And so now I want to act, so I act, in this case, one filter on all 256 by 256 regions. There's some issue of what I do with the edges. Do I let filters sort of go off the edge like this? Do I let them go off the edge everywhere? Or do I just let them go off the edge a little bit? This is really just a matter of choice, and it typically doesn't matter very much because what happens near the edges isn't that important for a big image. But up to issues like this, this takes my image and it applies some non-trivial filter everywhere and gives me some new, in the way that I've defined it here, it gives me sort of one new output after I've acted. Now, what was this C index that I added here? This C index could mean color. Typically, it's channel. So the strategy that I'll actually use to really fully process an image will be I'll act a bunch of filters on the image and get some new information, and I'll slowly increase the number of filters while I decrease the size of the image. So how do I decrease the size of the image? Well, there are a bunch of simple things I could do. One is I can just pool together neighboring pixels after I do this. So this is either called pooling. It's just this is maybe the thing in this world that's most similar to the RG. Physicists often ask about the RG when they hear about machine learning. I can take clusters of, say, 4 by 4 pixels, and I can, say, just take the maximum, or I can just more naturally take the mean of the pixels in 4 by 4 regions, and that's what pooling is. And so I'll go from a 256 by 256 object to a 128 by 128 object, and repeat the process. Another thing you could do instead of pooling, which maybe makes as much or more sense, is I can apply my filters with steps. So if this filter is 5 by 5, then I can slide it sort of 2 units at a time. And if I slide it 2 units at a time, then I cover the whole image in half as many steps as if I slide it 1 pixel at a time. And so naturally I reduce from 256 by 256 to 128 by 128. So, I mean, I can either use pooling or I can use what I mean, people use the word stride. I can have a stride of length 2 where I move these filters faster. And the strategy will be to increase the number of channels and decrease resolution until I do this many, many times and I shrink from, say, 256 by 256 through many layers to, say, 8 by 8, but with a lot of channels, in other words, with more and more of these filters. And then finally, I take the end result and I process it in some way to make a prediction of whether this was a cat or a dog or a yacht. So this is how convolutional neural networks work. And the huge benefit here is that we only have the number of parameters we have is equal to the number of channels times the number of pixels in the filters. And of course, you can put these together in all sorts of different ways. You can have some filters that are 5 by 5, some that are 3 by 3. You can have many of them or fewer of them. There's all sorts of different choices you can make. And this forms a huge class of families of convolutional neural networks that are used to process images. And so there's a lot of these actually have names, like there's Inception V3 is like the name of some particular choice of patterns of filters and pooling, etc. Residual networks were first applied in this context where they were used, where this, instead of having f of x, you have x plus f of x, was first used to process images and have many, 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 many layers. So that's another example. But this is the basic idea, is that you're taking advantage of translation invariance. And I think this has been applied. I mean, if you have a three-dimensional image, like if you have data that lives in a cube, you could very naturally have three-dimensional convolutions where you slide a filter around in 3 dimensions, etc. So that's what convolutional neural networks are. It's important to know what they are. They're just this fairly simple thing. So any questions about how this works?
You said that if you use stride, then you keep the same size of filter, but you just move it faster along the image?
Yes.
So if you keep the same size of filter and the same size of image, don't you have a problem with recognizing features which are larger than your filter?
So you mean if you keep the image the same size and never let it shrink, and never do anything sort of more non-local, then it's true that like the filter just does something locally here, and then when it's over there, it does something else, and these points never talk to each other. So that's one reason why sort of like shrinking the image, which you might think of, which might sound to you a little bit like the RG, is natural, because that allows you to first you sort of process over here and there. Typically the low-level filters, the first filters that act on the image, do things like detect edges and lines and things like that. Later level layers in the network detect more complicated things, like they put these lines and features together into like textures. And then later on you detect things like ears and the wheels of cars and things like that. So yeah, it is important that you that you eventually collapse this so that the information can propagate. Well, you either need to use pooling or some stride that's
But strides, well, maybe I don't understand what it is, but from what I understand, it doesn't shrink your image.
Oh, it is shrinking your image, because if your stride is 1, then that's just sort of the default thing that keeps the image the same size. But if your stride is 2, you apply the filter to this region, and then you apply it to this region, and then you apply it to that region, etc. And so since you've, say, applied it 3 times, but gone over a distance of 6 in pixels, your output, you have 3 outputs, even though you covered a distance of 6. So that means that you're shrinking the size by a factor of 2.
Oh, so you're taking that output
And you're just sort of making a new, smaller image out of it. So both of these accomplish the same thing. For some reason, I think this is more widely used, or at least it was historically. Any other questions? Okay. So now I'll try to use the rest of the time to talk about transformers, and a keyword related to this is attention. So, I mean, as actually you just asked about, something that you might imagine would be useful in great generality throughout this subject is being able to sort of select things out to pay attention to. So, in a more abstract setting, if I say I want to train a neural network to count how many cupcakes are in images, then I'd probably like it to be able to sort of look at an image and grab sections of the image that might contain cupcakes, and then process those further and figure out for sure whether they contain cupcakes and how many, and then tell me how many cupcakes there were in this picture. So it'd be nice to be able to sort of highlight things that are important and upweight them and gather them together if necessary, and ignore other features, and to sort of move things around. I think this is an obvious thing that we intuitively do. That's the sort of basic idea of transformers, is to operate on images in principle, or I mean, I think the more natural example would be sequences, by paying attention to what's relevant, or learning to pay attention to what's relevant. So, for example, when in this sentence I wrote, let's say I have a sentence 2 blank, there's some word that's going to come up here, and what this word is likely to be probably depends on the fact that I'm talking about sentences. So I'm going to do something to sentences, and I have them, if I can go back further, it might refer to the fact that, like, the title of this talk was machine learning, and so maybe in machine learning I like to model things. And so when I'm at this juncture and I'm trying to figure out what the next word is going to be, I'd like to collect together sentence, and I'd like to collect together the fact that this is a lecture on machine learning, and I'd like to get that information together, and probably the word let's sort of doesn't really matter very much. This is just some grammatical thing. It's not really doing much to tell me what I'm about to do to this sentence. So what I'd like is some mechanism that can learn to gather together that information right here when I'm about to make that prediction. So that's a very concrete example of wanting to have attention. And this might be powerful because it doesn't suffer from this issue that we had with the recurrent neural network, where if it's remembering that this is a lecture about machine learning, it has to remember that through all of these words until it gets to here. So it'd be nice to have a mechanism that does that. So remember, we have this V0 embedding, V1 embedding, etc., to V7 embedding, which are these vectors. Another way of motivating transformers that I think is also reasonable is sort of much more agnostic, which is just like, I have all of these V's that I just wrote over there, and I only have 8 words in that sentence, but if I have 1,000 words, then I have 1,000 of these V's. And so I'd like to find some kind of tensor structure that I can act on with these V's that doesn't have too many parameters, but still does something non-trivial that sort of works across different V's and works within the V's, right? So if I had one gigantic matrix that was 8 by 256 on a side, then I could just concatenate together all of these V's and act on them all with one big matrix. But that would be annoying because this becomes a big number very quickly. So I have these 2 tensor indices. I have this sequence index and this embedding matrix index, and they both range over quite a bit. So I'd like to find some interesting mathematical operation that allows me to do something non-trivial in both the embedding vector space and in the sequence direction vector space without gigantic matrices. So those are 2 sort of different ways of looking at this. I mean, from this latter way of thinking about it, you could just sort of write everything down that you can, right? I mean, like, you'd start writing down V, S, E, and you could say, well, what can I do with this? Well, if I'm limited to linear operations, all I can do is act on E or S. Maybe I can mix them up in some horrible way, but basically I can only act on S or E. So you might say, oh, well, maybe I can do something interesting and nonlinear, like I can do V, S, E, V, S, V prime, E prime, and then I can like contract together E with E prime, so I can make up some matrix M, E, E prime. And now it contracts together these, and I'm left with only the S and S prime index, and I can do something like that. So if you follow your nose this way, you can write down some simple functions, and one of them will be what the transformer is. But of course, it's probably more natural when talking about it at the end of the day to refer to this idea of attention. Okay, so what do I do? How do I talk about attention? Well, at this position, I want at, say, position, well, this is position 6, so I'll just choose it. At position 6, I want to grab some sigma 6 comma j, sorry, I should call this S prime, V S prime E. So this is, I mean, just to be clear, I'm always using Einstein summation convention, so this is 6 comma S prime. And I want this to be sort of the, this is telling me relevance, right? So when I'm at the location of 2, trying to figure out what I'm going to say for model, I'm at 2 because I predict the next word, so I'm at 2. I'd like to somehow grab a linear combination of all of the other V's, weighted by how relevant they are to what I think I need to do next. Okay, well, this is already in some sense progress, because now I just need to figure out what to do to compute sigma. So this is relevance. So it would make sense for it to be a bunch of numbers between 0 and 1 that say add up to 1, and they're big when there's a lot of relevance and small when not. So how do I compute that? Well, in order to figure out what's relevant, so to determine relevance, I need a question or query about V6E, and key to tell me relevance of the S prime to the question. So this is just terminology that's used. Query is used and the key is used in this attention process as a way of talking about these relationships. So how can I do this given that like linear algebra is all I really want to have to do plus some simple functions? Well, I can make a key which is some WK KE VS So for all of the vectors V in this sequence, I can make some key by just defining some matrix WK, which is a projection onto keys for all of these vectors. And I can make a query in the position that I care about. So I'm at 2, which is the sixth letter, K, which is just some W query, K E V S E. So now what have I done here? Well, I've projected into some possibly smaller vector space indexed by K with this WK and this WQ to try to talk about relevance. And so relevance will basically just be, I mean, this is slightly squiggle, will basically just be key s k dot query k, well, 6 comma k, since I'm focused on 6. So the inner product of the key vector in position s with the query vector in position 6 will tell me how relevant the word at position s is to the question I'm trying to ask about position 6. This is nice because, I mean, I've just defined some matrices which are at biggest sort of like 256 by 256, and if the k direction is smaller, which it could be, then these are even smaller matrices. So relevance isn't quite this because I wanted it to be between 0 and 1, and this is just some real number. So I can do the usual thing, and I can apply softmax to this. So in other words, really relevance is going to be e to the key s k query 6k over the sum on s prime of e to the k s prime q. So this function just transforms me from real numbers to these sigma 6 s's. So I wanted to figure out this relevance, and now I have something that computes a relevance. And this is the way attention mechanisms work. This is usually called self-attention because the words are just paying attention to the words. You could imagine using this whole mechanism for all sorts of other purposes. Like if you're asking a question about an image, like I mentioned before, like how many cupcakes are in an image, then your query can have to do with how many cupcakes are in the image, and your key can be something that runs over the image and selects out relevant things. But here, it's the vector space of VSE paying attention to itself, so it's called self-attention. So this is the key ingredient in the transformer. It's not the entirety of the transformer, but it's sort of the key idea and the key ingredient. So questions about this attention thing. At the end of the day, you can write this. I mean, I was almost about to write this here. This is some multilinear operation, which is softmax v s e w q e k w k k e prime v s prime e prime times v s f. So, I mean, I just wrote some tensor thing with Einstein's summation convention, which takes two v's in order to figure out the relevance of s to s prime, and then applies that as a linear combination. Maybe I want to call this s prime. In order, this finally gives me some vector. I don't know. I can call it y f at the position s. So, like I said, if you were just to sort of view this as some problem of like constructing some tensor that can multilinearly act on V to sort of move information around, given this factorization of V into sort of sequence position and embedding space, you could just start writing stuff down. I think you'd quickly learn that there isn't anything that interesting that only involves two V's, and then once you wrote three V's, you could make up some matrices, and voila, you have something like this. So this is kind of like a clever way of combining things together. If you can think of something like this that's different and that acts in a different way, but is some similar function, maybe it's an interesting neural network architecture. think mostly we're constrained by simplicity and not wanting to have a ton of parameters. So now, so far, all of our parameters are there and there. So any questions? Good. How much time do I have? 10 minutes? Okay, cool. So there are a couple of elaborations on this that are added in order to make the full transformer. So one elaboration is that you might ask, why did I make this K different from E? I could have just made these square matrices if I wanted. But what's typically done is each of these, the process I just described here is referred to as one head of attention. The word head is supposed to represent kind of like, maybe like a Turing machine head or something. I'm looking at two, and I might want to have many different sub-processes. One that, say, looks at grammar, and so it tries to figure out whether the next word is a verb or a noun or whatever. I might want to have another one that tries to like figure out what the style of the sentence is. It notices that I said let's, and so it thinks that the sentence is informal. I might want another mechanism that looks through and asks just like logically, like what is it likely to be, given that I was referring to sentence. And so you might think that it's nice to have sort of several different things iterating over the sentence and selecting out different features. And so each of those things is called an attention head. The reason why I made this K different from E is because I can have, say, maybe I have 6 heads. I'm just making up numbers as usual. And so I can make the key query dimension equal to 256. Oh no. Say I make there's 8 heads, 256 over 8. And so I can have 8 heads that each only use sort of an eighth of the vector space. Then I can assemble, how do I assemble the information back together? Well, I wrote this as a linear combination with an E index, but I can always add some extra matrix here, which is WV, this is the typical notation, E comma K, and therefore each attention head doesn't select out the entire vector that it grabbed, but instead it selects out some subspace of that vector that's relevant to its particular operation. Then, when I'm done, when all of these attention heads have gathered together the interesting information from earlier in the sentence, they can just be stacked together, so these get concatenated together, and I get some final output. So multi-headed attention is a term that you'll hear, and that just refers to this process. And that opens a question, as always, with these things, like how many heads should you choose? The answer is it doesn't matter all that much, but it's just an empirical question. The other feature that the transformer model has is now we can write sort of what's happening to our sequence. So we have these vectors we can act on them with multi-headed attention, and that gives some processed information, but all we've done is sort of gather the information together. We've sort of grabbed things that we care about. We haven't really processed it, so typically there's another step, which is to just apply a fully connected layer to each V. So in other words, this output, this complicated thing, gets hit by our friend max 0 WV plus B. Typically it gets hit by 2 of these, so there's some W2 and some W1. And finally, the other thing that's usually added is there's usually layer norm and this is usually a ResNet, it's usually residual. So typically, all of these operations are applied, and then you add the result to the original input so that you sort of preserve the original information. That's what's typically done. But if you put all of those ingredients together, that's one layer of a transformer. And so I think there's like a, there's some website like talktotransformer.com that does language modeling, and you can play with it. You can enter text, and it'll write more text for you. And that's probably a transformer with something like 30 or 40 layers. And the dimension of this E vector space is probably order 1,000 or 1,500. I know the full network has like a little more than 1 billion parameters. And so this is sort of how transformers work. And so the nice thing here is that if you have a 1,000-word sequence, there's nothing stopping the network from grabbing information from 500 words ago and pulling it up here if it becomes relevant. And so you can get very, very long context information into the result. Which means that like if this model is writing paragraphs and paragraphs, then they can be coherent over that whole range. So there are a few other details. You can also, a very nice exercise is to try to count how many parameters this whole neural network has in it, say per layer. There are all of these W matrices, there's some number of heads, there's also some matrices here in this fully connected layer and blah, blah, blah. Counting how many parameters there are and say how many computations occur when this acts just sort of forces you to really understand everything that's going on. I think if you can count how many multiplications and additions occur, then you basically must know sort of how the network works. So I think I'll just stop here and take questions. Yeah.
It's more of a general question. So what's some good intuition to take from physics and apply to neural networks?
Good question. So I think there's a lot of intuition. I mean, I made fun of it, but I think there's a fair amount of intuition about optimization. For example, there's this question of the effective temperature at which you're doing optimization. That has to do with both the learning rate, like how big the steps are that you're taking. It also has to do with how noisy the data is. So I think there's a bunch of things from that. There's a lot of very interesting work being done on the large width limit of neural networks, which I mean is kind of like a large N expansion. It's really very, very much like a large N expansion in the following sense. So if a neural network layer is very, very, very wide and it's randomly initialized, then there's a huge number of random numbers that are being multiplied by a very large dimensional vector and added together and to give you the output. And in the limit that the width of the network goes to infinity, you get pure Gaussian statistics, because if you add n independent random numbers together, whatever their individual distributions, the central limit theorem says that you get something that's Gaussian. And if n is finite, then you're not quite in the central limit theorem's domain of validity. And so instead of something purely Gaussian, you get some small correction of order 1 over n. And what that means is that a free quantum field theory is something, or an infinite n quantum field theory, which effectively acts like a free theory, is the same thing as just sort of studying Gaussian statistics. So this is really exactly the same thing. Like Ethan Dyer and Guy Guerrieri, in fact, have a paper sort of showing that this is that there's some Feynman diagram expansion for some properties. So there are limits like that I think are very nice. Another situation, so I mentioned this issue of number of parameters versus number of data points, and then you can have far fewer or far more parameters than data points, and there's some transition that happens. There's some formal sense in which there's a phase transition versus when you compare when you scale number of parameters versus number of data points in some regime. So there's some work on that. I think there are other sort of phase transition like ideas. So since the number of parameters and the number of data points are all very, very large numbers, I think you're totally reasonably in some kind of thermodynamic limit. So an example that I've thought about a bit is what happens when you're learning versus memorizing. So there isn't necessarily in all cases a sharp distinction between those two things, but I think in some cases there is, and there's a kind of phase transition between overfitting and actually learning in a way that generalizes, and a lot of features sort of change this continuously. I think there's some cases where this is a super sharp idea. So I think basically there are a lot of ideas from statistical mechanics and perturbation theory, because perturbation theory is almost always an expansion around the harmonic oscillator, and the harmonic oscillator is just something with Gaussian statistics that apply. And it's really just a matter of taste, sort of how you want to think about it. I mean, you can try to find the thing in this subject that's as close as possible to physics, and sort of then you can talk about it very much in physics language, or you can sort of dive into the middle and ask, like, what are the patterns that you see, and can you sort of understand them? And I think both are reasonable. I mean, I can go on and give you other examples. I don't think there's a unifying theme except kind of like statistical mechanics-ish thinking is very relevant.
Further questions for the break since we're running a little behind. So let's thank Jared again. Let's meet again at 3:35. 4:35.